Very correct.
Okay, so yeah, it's a bit slow today. So maybe what we're going to do, let's just download the presentation. Let's download the presentation so that we have, I'll just be telling you the slide number because now we're moving very slow. Okay, so we're on slide okay, let's get to the slide that reads multiplication rules. Let's get to the slide that reads that multiplication rules. Are we there? Are we there on the multiplication rules?
Yes, we are there.
Okay. So, so if we cross multiply, okay, so on that slide, we are told, you see that formula, probability of event 1 intersection event 2 is just equal to probability of event 1 multiplied by probability of event 2 given event 1. So this formula is obtained from the conditional probability formula. So in that case, we first had a probability of event 1 given event 2. So with the probability, the conditional probability formula, you get your equation, and then that is using the conditional probability formula. So after that, then you cross multiply, just as we did for the probability of A given B. So I'm sure we're able to derive that formula. So we can use that formula if we're given the probability of event 2 and the conditional probability. Then we can use it to find the intersection. Okay, so do we still remember the test for independency? If E1 and E2 are independent, then okay, the slides are moving quite slowly. Okay, so we are now here. This is the slide that we're looking for, the multiplication rules. Okay, so we use this formula when we need to find the intersection given the probability of E1 and the conditional probability. Okay, now just the previous one, event 1, again, it's taking some time. So event 1, two events E1 and E2 are independent if the probability of event 2 given event 1 is just the probability of event 2. So this is the formula that we use. It's in the previous slides. We're able to see that. Okay. Okay, still the slides are quite slow today. Okay, maybe we can go back to our slides since we are able to download. We are able to download the slides, so we can just use our downloaded slides. Okay, so just check the previous slide, which says that the probability of E1 given E2 is just equal to the probability of E1 if E1 and E2 are independent. Then we came to the multiplication rules. What we're saying is that if we are given the probability, the conditional probability and the probability of E1, we can use it to find the probability of the intersection. And
Madam,
yes,
this topic is written to be what on the slides. I want to download the slide.
it's written lecture 4, probability and probability distributions.
All right, thanks.
Now, not that, okay, thank you. Not that, so you mean you can't download from this platform? You can just, there's an arrow down to your left, down there. You can use that arrow to download the presentation. Have you seen that arrow? Okay, so have we seen that arrow? Down there, that's the arrow that you can use to download the presentation. Okay, so we note that, and again, probability of E1 and E2 is just the same as probability of E1 intersection E2. So it's just the same as that formula there. This formula changes to probability of E1 multiplied by the probability of E2 if these events are independent. What is going to happen to this probability, the conditional probability, if our events are independent? The probability of E2 given E1 for independent events, what is it equal to? I'm waiting for answers. If in two events are independent, what is the probability of E2 given E1 going to be?
0.
Yes, we can get you. Yes.
Can I try?
Yes, you can.
Is it going to be the probability of event 2?
Yes. So actually, this is the test for independence. For any independent event, probability of E2 given E1 is just going to be probability of E2. So that is the one that is replaced there, because we know for independent events, this just becomes probability of E2. You find that the probability of the intersection of two events just becomes the probability of the multiplying the probability of the individual events. Okay, so that this is why we even for independent events, it's very clear even for tree diagrams. We just multiply the probabilities of those events that we have to find the probability of the intersections. Okay, so let's just go to the next slide from our downloads, because again, it's taking some time. So from the downloads, the next slide talks about tree diagrams, and it gives us the previous, this example, I think we had done it. Now from here, we just see that the probability of E1 and E2 is just the probabilities of the the branches. Like for gasoline, we had 0.8. So the probability of E1 and E3 becomes 0.8 multiplied by 0.2. So you just multiply the probabilities of those events on the branches. Okay, so we'll see, I think, a better example on tree diagrams. Now, I want us to do some few examples. Okay, so actually, let's do this. Okay, I'm going to share my screen. Okay, so I'm sharing my screen. I hope it comes up. I wanted to use a different book for the Bayes theorem. I think it explains it better. Okay, so on the conditional probabilities, I think we did quite a bit of examples from the last time. Now, most of these probabilities that we have calculated are called priori probabilities, because these are probabilities that are obtained when an event has already occurred. Okay. So, or we use the fact that the event will occur to obtain the probability. But what about in an event that event has not occurred? An example is, okay, maybe before an election takes place, what is the probability that an independent candidate is going to win? How can we calculate that probability? Okay, so in that case, we use the Bayes theorem. Okay, so there's I'll just mute Brighton's mic for now.
Madam, you've muted yourself.
Is not muted.
We can't hear anything.
Madam, your mic is off.
Technology chat.
Ma'am,
Okay, so the screen should now be shared. Okay, so let me just make it wide. Okay, so you can just make the screen to be on full screen. Okay, so as I was saying earlier, sometimes you want to find probabilities of events that have not taken place. Okay, for example, in an election, so I'll use odd parties so that I'm not quoted. So I'll use MMD, I'll use UNIP, and FGD. Okay, so suppose we have 30% of the people who claim to be MMD, okay, and 40%, so 30 are claiming to be MMD, and 40% are claiming to be UNIP, and say, so 30, and another 30 is claiming to be FGD. Now, if an event takes place, what is the probability that if we pick a random voter, that person belongs to MMD? Okay, so what we are doing is that we just know the probabilities of those that belong to, say, MMD, FDD, or UNIP. But what if we pick a random voter? What probability is it that this person voted indeed for MMD or voted for UPND? So in that case, we use the Bayes theorem. It is what we used to find the posteriori probabilities. Like this just defines the probabilities that have not yet taken place. Now, in this example, this in the paper that's there that I've put across, they're trying to test some machines that produce engine components. Okay, so now we are told that suppose 3 machines, A, B, and C, produce similar engine components. Okay, machine A produces 45% of the total components. Machine B produces 30%, and machine C produces 25%. For the usual production schedule. Oh, no, 25%. For the usual production schedule, 6% of the components produced by machine A do not meet the established specifications. For machine B and C, the corresponding figures are 4% and 3% respectively. One component is selected at random from the total output and is found to be defective. Okay? What is the probability that the component selected was produced? Okay. Okay, so what's the probability that the component selected was produced by machine A? No, I'm telling you to scroll. Okay, so we are looking for that probability. What is the probability that the component selected was produced by machine A? So what are we going to do? In this case, what are the probabilities? We first identify the probabilities that we've been given. Okay, so what is that 45% from machine A? It's just the probability of producing a component, right? An engine component. The percentage, yeah. So machine A produces 45% of total components. So this is just the probability of machine A, right? And what is that probability given in percentage? What's the probability?
0.45.
0.45.
Okay.
0.5.
And the probability, okay. And the probability for machine B is
0.3.
0.3. Probability for machine C, 0.25, right?
Yes.
Okay. So the ones that have been given now, they say it's from the sentence that says, for the usual production schedule, 6% of the components produced by machine A do not meet this established specifications. Now, suppose that not meeting the specification is being defective, then the probability that we're given is that it is defective coming from machine A, right? That is the probability of D given A, where D is being defective. So D is being defective. So the 6%, the 6% that we've been given is the probability of D given A. It's defective and coming from A. So that is 6% and it's 0. What? 0.06, right?
0.06.
And we have the probability of D given B, right? It's defective
Sorry,
and
madam,
coming
could
from
you
B.
hello?
Yes.
Could you kindly repeat the explanation you gave for the 6%?
Okay, so the 6%, we are told that for the usual production schedule, 6% of the components produced by machine A do not meet the established specifications. So now we are trying to see what this 6% is. So this is the probability that it doesn't meet the specification and coming from machine A. So we can say not meeting the specification can be defined as being defective, right? So this is the probability of D, defective in this case is D. So we're going to say the probability of D given A, 6%. And the probability that is defective and coming from B will be 4%, which is 0.04. Yes, and the probability that it's defective and coming from C is 0.03.
0.03.
Now, yes, our question is asking us to find the probability that the component selected was produced by machine D. Actually, it says from one component is selected at random from the total output and is found to be defective. What is the probability that it is coming from machine A? So what we are looking for is the probability that it is coming from machine A, given that it is defective. Isn't it? It's coming from machine A, given that it is defective. This is normal conditional probability. What is the formula for conditional? Probability of A given D. What is the formula?
Is it probability of A given D or D given A?
Remember, D given A is already given to us in the question.
Okay.
So we cannot be asked to find, we cannot be asked to find D given A. We already have it. It's 0.06. So now this is the probability that it is defective coming from machine A. So this is the one that we have been asked. So what is the formula for that? According to conditional probability.
A given A, A given D.
A given D.
It's going to be A.
What is the formula?
Probability of A intersection
Probability
D.
of what?
A intersection D.
D.
D over what?
D.
Over probability of D.
Yes. Okay. Now remember, we don't have the probability of A intersection D. You see that, right?
Yes.
But we have the conditional probabilities and we have the individual probabilities. So remember the multiplication rule. We use the conditional probability, right?
Yes.
You remember it now, right? We don't have this intersection. Okay. So somehow we have to get it. But we have the conditional probability. We have probability of D given A, and we have the probability of A. So from the conditional probability of D given A is just probability of D intersection A, right? Over probability of A, right? Cross multiply that, you'll find that probability of D intersection A is just the probability of A multiplied by the probability of D given A. Are we together?
Yes.
Yes.
Are we together?
Yes, we are together.
No, madam, you've lost me. In the question it said, for the usual production schedule, 6% of the components produced by machine A do not meet established specifications. So you said, for the defectiveness of machine A, it will be given as 6%, correct?
Yes. So that is probability of D given A.
That's the
It's
probability of
defective
D
and
given
coming
A from
Yes.
A.
defective coming
Just
from A.
defective.
Yes.
So its probability will be what? 0.06.
Yes.
Yes.
Okay. So now, what are we finding now? Are we finding the probability of D given A, or because I feel we already found it? So are we finding the probability of A given D?
Yes.
So we are there in finding probability of A given D, but the formula, the numerator, we are just establishing how to find the numerator, which is probability of A intersection D, because we are not given.
Yes.
So
So
we are not given A intersection D. So we can use the
correct.
conditional probability and the probability of A to find that probability.
So the formula will be the probability of A given D will be equal to the probability of A intersection D over the probability of D.
Yes.
Yes.
Okay, then we cross multiply from here.
No, we're not going to cross multiply, because the probability of A given D is what we are looking for. Okay. So we just need to find this A intersection D and divide by the probability of D.
Oh, okay. I think that's where
that we have.
Pardon?
Probability of A intersection D can be gotten from the data that we have.
Which
Remember
is
the multiplication rule? Let's just deal with the numerator for now. Let's deal with the numerator, which is the probability of A intersection D, right?
Yes.
Yes.
So what we're given in the question, remember, is probability of D given A. So the probability of D given A, according to the conditional probability formula, is just the probability of D intersection A over A, right? Are we together?
Yes.
Probability of D given A, what you do is that you've already written the probability of A given D. Just write it on the corner and leave it. Okay. Then come to another corner, start doing what I'm now saying. We are dealing with the numerator for now. We want to establish how to find that. Okay. So what I'll do, I'll get my probability of D given A. I know that the probability of D given A is just the probability of D intersection A over A. Are we together there?
Yeah.
Now, remember, this is D intersection is just the same as AND, right? So D intersection A is just the same as A intersection D, right?
Yes.
Yeah.
So the probability of D given A is just the same as the probability of A intersection D over the probability of A, right? Now we cross multiply and we're going to find that the probability of A intersection D is equal to the probability of A multiplied by the probability of D given A. Are we together there?
So D given A is this one. Okay.
We're together?
Yeah.
Yes.
Are we together? We are. So that means that, but remember, this A intersection D is our numerator. Okay. So on the numerator there, we can find it as probability of A multiplied by probability of D given A, which we have, isn't it?
Yes.
Mhm. So this is the key. That's the main part of the Bayes theorem. So now that we have the numerator, we just have to establish the denominator. Okay. Then the denominator is the probability of G.
Sorry,
So
madam,
in
for
this
taking you
case,
back. Could you maybe write it on the board behind you? Because I'm just hearing people saying yes, yes, and they're not turning off their mics. So I don't know what what they are saying yes to.
okay, so let me see if I can share. Okay, let me see. Let me do this. The problem is that the PC is not. I cannot write.
Brighton, zoom your mic.
Okay.
Okay, so maybe we can have this there. I don't know if you can see it in what we have there. Is that the probability of A given G is just the probability of A multiplied by the probability of G given A. Do we understand how we come up with that? That's what I was trying to explain. Do we?
Yes, because that one comes from the formula that we are earlier given for the conditional probability. But as my
Yes.
friend suggested, that board that is behind you, it's very clear and we can see it. So if you can scribble something, it will help him understand.
Okay, now the problem is that I need a touch or a touch screen for me to be able to write, or if I use something that has a pencil, but I'm not using that. So the PC is limited. Let me see from just Adam.
Madam, so we are talking about the board in your office there behind you. Maybe you could use a marker. It's clear enough. Yes, it's clear enough for us to
the
see.
board.
Yes.
You're talking about the board. I thought you're talking about the screen.
No.
The screen. Okay, just a moment. Let me just grab a marker.
Thank you. Thank you so much.
Okay, maybe. Oh, let me just.
Hello.
You are now unmuted.
Can you see? No. I think there really needs to be.
Adam, we can see clearly. I don't know if you can hear me. But your mic is off, madam. Oh, wow. Madam, your mic is off. Sorry.
We can't hear you.
Nothing? Still
Can't
nothing.
hear you, madam.
Maybe try removing the headset.